Hello everyone, thank you for being here. I'm Samyukta and I'm a senior research scientist at Amazon. I'm part of a team called Pros. Our team works with multiple business units across Amazon to solve problems using machine learning, OR, and data science wherever applicable. In this session, I'm excited to share with you our learnings from using a combination of machine learning and mathematical optimization to improve the experience of millions of Amazon customers in Amazon lockers. So a quick look at the outline for today's talk. We will start with the what, where, and why of Amazon lockers and locker capacity management. We will understand a business problem that the locker business was facing, followed by a root cause analysis of the problem, a solution methodology formulation to alleviate the root cause, finally the solution itself and results and what lies next for Amazon locker capacity management. So coming to the what, where, and why of Amazon locker. I'm sure many of us here today have used an Amazon locker or at least seen one. But to bring everybody on the same page, an Amazon locker is a self-service delivery or return location. It looks like the image here or the mock-up locker that we have here. It's free to use. When a package gets delivered to a locker or if a customer places a request for a return to a locker, Amazon sends a QR code and a 6-digit code. So I can either go and scan the QR code or type in the 6-digit code at the locker and retrieve the package. The package needs to be picked up within 3 days, and if it is not, then it is returned to Amazon with no charge to the customer. Let's look at a video by an external customer reviewer that shows how a locker is used.
One of the most frustrating things about ordering online is the fact that the parcels often get delivered to your home when you're out at work, paying for the things that you've ordered online. Well, Amazon have a solution to this, and I'm going to show you how it works. The idea is that when you're putting your order in on the Amazon website, instead of your home address, choose a pickup location instead. Put in a postcode and it'll tell you if there are any lockers in your vicinity, and if so, get it delivered there instead. Now, I've got Amazon Prime membership, which means this locker facility doesn't cost anything extra and I get next day delivery. If you don't have Prime, you're going to have to pay extra for this. Anyway, I get an email while I'm at work at lunchtime telling me my parcel's arrived, it's in my Amazon locker, I've got to go and pick it up, or it'll be sent back to Amazon after 5 days with a full refund. Right, so I've got my phone with me with my pickup code. So all I need to do now is go and put that in the Amazon collection point inside my local co-op shop. So let's go and have a go. I can see why Amazon chose to link up with Co-op for this, because the Co-op shops tend to just do groceries. They don't really cross over with any of the products that Amazon sell, so there's no conflict of interest, and also there's one in most towns. As you can see, the Amazon locker's got all sorts of different shapes and sizes of doors, and it's quite deep as well, so you could get some quite big parcels in the bottom of there. Anyway, my Amazon locker is called Peach, apparently, and all I have to do on Peach is put my pickup code into it that I got on that email, and that will mean that a door will open on this. You can always play a bit of a guessing game. What's the number that's going to pop open? Ah, there we are, number 24. Right, so there you go. That is the thing that I got delivered. Popped into the Amazon locker, close the door, that's it, sorted. And it says thanks for using the Amazon locker. Right, so I could just go home now at this point, but of course the good thing about being in a supermarket is I can also do a little bit of shopping while I'm here as well. Pick up the odd essential. Anyway, that's it for the moment. Thanks for watching.
Okay, so now that we are all caught up to date on what an Amazon locker is and how it is used, let's go on to where they are located. We had an Amazon locker at the music festival Coachella this year. Attendees found it so convenient and easy. There is an Amazon locker at the Louvre in France. More commonly and generally, We have them at shopping centers, business parks, office buildings, convenience stores, gas stations, highly frequented locations. Currently, we have lockers in the US, UK, and European Union countries. As a fun exercise, let's look at where our Amazon lockers are near us right now. So we are in zip code 89158, which I can go type in. Oh, so there are a lot of locker locations near us. If any of us forgot to pack something, we can order that to the Amazon locker here in Vegas and get it delivered there. Okay, so coming to why would someone use an Amazon locker? Theft protection is a big reason. There have been instances of packages being stolen from outside the front door. This is a tweet by the Bloomfield Division of Public Safety advising their constituents to order parcels to Amazon lockers to prevent package theft. The other reason is our customers can choose when they want to pick up a package and where they want to pick it up from. This customer here is ordering her bachelorette party items here, to a locker here in Vegas. When I lived in an apartment complex where the leasing office was only open from 9 a.m. to 6 p.m. and I used to be at work between 9 a.m. and 6 p.m., I could either wait until the weekend to pick up my package, or the more convenient option was to order it to an Amazon locker in my building, office building. Coming to locker capacity management, the what and why of it. Let's look at another zip code where lockers are in high demand. So I want to look at a zip code in San Francisco downtown. So here we see a bunch of locations that are grayed out and some that are not grayed out. For the grayed out locations, it means that we are predicting that when this package will arrive at the locker will be full and there will be no space for the package. And so our order cannot be placed for delivery to that locker. Let's look at one location that is not full. So let's look at this one. We have two ship options here, a 2-day delivery and a 1-day delivery, and the free locker delivery. Let's look at another locker in the same zip code. And we have more options here. We have standard delivery, 2-day delivery, 1-day delivery, and the free locker delivery. So why would we have more options in one locker and less ship options in another? So the reason is this. At the beginning of each day and for the next 7 days, we reserve capacity for each ship option and for each day. If we consider this table to be an Amazon locker with 36 slots, we might say that for today we have reserved 15 slots for 2-day ship options, 8 slots for standard ship option, 4 for same day, 2 for next, and 2 for returns, and we want to leave some slots free to be allocated on a first come first serve basis. Now why do we need to do this? Let's consider a delivery day that's 5 days from today. And let's consider a hypothetical locker with just 4 slots. In practice, we have more than 4 slots, but to make the problem simple. So today, let's say that there is a request, a standard shipping option request for a package to be delivered to the locker 5 days from today. and we accept this because we have space in the locker on that day. Another request comes in, we accept that as well. Another standard shipping request comes in, that also gets accepted, and the fourth request for standard shipping option also gets accepted. Now let's say that one day before the delivery day, there is a request for delivery of a prime ship option package. We don't have space in the locker anymore, so we have to say that unfortunately this locker is full and you cannot place your order. But this customer paid for prime shipping to be able to order closer to the delivery day. And this is definitely not fair on the customer, which is why we need those reservations. So a first come first served policy would result in rejection of prime shipping options while prioritizing standard ship option packages. And this is not what we want. On the other hand, what happens if we reserve too many slots for prime packages? The first standard ship option package request comes in, we accept it. The second one gets rejected because all other slots are reserved for prime packages. Third one also gets rejected. Fourth also gets rejected. And finally, we accept the last prime request because we reserved space for it. But on the delivery day, we now have 2 slots empty and wasted when we said no to 3 customers. This is again not what we want at all. Reserving too much capacity results in underutilization of locker space and very poor customer experience. And this is definitely not appreciated by our customers. What the ideal situation here would have been was to reserve 1 slot, accept the first standard shipping package, the second one and the third one, and not accept the fourth one, finally accept the prime package. But there are challenges to doing that even in this simple scenario. How do we know that an order will arrive for a prime package 1 day before the delivery day? We need to make a decision on accepting or rejecting the standard ship option package 3 days before the delivery day. And in all this, we haven't even considered the fact that packages can stay for longer than a day. And that adds another level of complication. Capacity management has become important and will continue to become more and more important over the years. And this is why. So this plot is the blue line represents the number of locker deliveries, and the green line represents the number of lockers normalized by the number of locker deliveries and the number of lockers in 2016. So if we consider the ratio of number of locker deliveries to number of lockers in 2016 to be 1:1, the ratio has increased by 5 times in 2018, and it is going to increase by more than 25 times by 2021. And why this is important is because consider a 100 slot locker, and if you have demand for only 10 packages in that locker, you don't need any capacity reservation. We can just accept all the packages. But if we have a 100 slot locker and if we have demand for 110 packages, that is when we would need capacity reservations. Let's take a look at how these reservations impact real-time decision making. So a request comes in, can you deliver my 2-day ship option package to locker Ruby? Ruby is a locker in the South Lake Union campus of Amazon in Seattle, and the order request comes in today. We predict that this package will be delivered tomorrow and it will stay in the locker until for 2 days. We then look at how many packages have we already reserved, how many packages have we already accepted for delivery to the locker. We add this new locker reservation to that and check if that number is less than or equal to the capacity that we had reserved for 2-day ship option packages. If the answer is yes, then we accept, and if it is no, then we have to say that we cannot accept the package for delivery to this locker. Now that we know the scenario, we know what Amazon lockers are and why we need capacity management in these. Let's move on to a business problem that the locker business was facing. We had this whole process that was going on, and let's say that we said no at the end of the process, and we predicted that we will not have space. We saw empty locker space on the days on which the package would have been in the locker. In fact, in 2017, we rejected 20% of locker requests, and out of that 20%, between 18 and 35% were unjustified rejections, meaning that we had space in the locker, but we still said no to our customers. Our customers definitely did not appreciate it, as evidenced by this. Or this customer who is hesitant to order things from Amazon because she cannot place returns to a locker. So we looked at what might be the causes of these unjustified rejections. There were multiple causes. Each person we spoke to had a different idea of what might be causing this, and it turned out all of them were true, just that different causes had different level of impact. And the major cause was incorrect ship option capacity reservations, the reservations that we saw earlier. We were rejecting packages and reserving too much capacity for prime packages. So we looked at the methodology that was being followed for these ship option reservations. How did we come up with those? And this was the process. Let's consider this zip code 89158, and for a particular week, let's say week 12 of 2017, we saw 3,000 two-day packages and 1,000 standard packages hypothetically, and these are deliveries to homes, not to lockers. For the same week in 2018, week 12, and in the same zip code, if we had a 100-slot locker, we would reserve capacity in the same proportion. So we would reserve 75 slots for two-day packages and 25 slots for standard packages. And why was this not working? It had some underlying issues and assumptions. The first one was constant locker demand throughout the week. So this is a plot of actual versus predicted. The blue line is actual and the orange line is predicted number of packages in locker Ruby over 1 week in April 2018. And it is clear that the prediction is not able to capture the variability over the week. The second assumption was the equal proportion assumption, and that was also not true, because again, looking at another locker Lambda, which is in LA, the two are not even close to each other, the predicted and actual. The third assumption that we had was we were assuming that packages would get picked up on the same day as delivery. This is a plot of the percentage of packages that got picked up on the same day as delivery, which means that dwell days, number of dwell days is 0, and 1, 2, and 3. And we see that up to 55% of our packages get picked up on the same day as delivery, but there is this other whole 45% that we are not even considering. The last and most concerning for me was the fact that we did not have any objective defined. Should we reserve 5 slots in a locker? Should we reserve 10 slots? Neither could be right, both could be right, nobody knows, because there is no objective. So before we go into how we formulate the solution, let's have a quick recap of what we saw so far. We understood the business problem, which was unjustified rejections. We were saying no to customers when we had capacity in the locker. We identified different causes and their corresponding impact. And we identified the cause that was causing the maximum number of unjustified rejections. And we looked at how what was causing this cause. So we looked at the underlying issues, which included wrong assumptions and the lack of an objective. That brings us to the formulation of a solution methodology that would alleviate those issues. The first question we asked was, what is our business objective? Is it transportation cost savings? Because transportation cost savings is a side effect of lockers. If we are delivering more packages to the same location, so we are saving money on transportation costs. Or is it to improve customer experience? And unanimously we were all aligned that locker as a business exists because we want customers who are not able to place an order for delivery to their homes for any reason to still be able to use Amazon. And we quantified that by saying we want to maximize the number of packages delivered to lockers. There are always constraints to that, why we cannot accept all packages. The first one was the number of packages that get delivered minus the number of packages that get picked up to a certain day should be less than or equal to the locker capacity. And we want to reserve only as much space as the demand. So the number of packages accepted for delivery should be less than or equal to demand. After defining the objective and the constraints, we were able to identify decision variable which would tell us how much capacity to reserve, which was number of packages accepted for delivery to the locker. And we were also able to identify the unknown parameters here, which is demand. We don't know what the future demand is going to be, and the number of packages that get picked up, because we don't know how long a package will stay in the locker for. That depends entirely on the customer. Along with this, we also defined the business performance metric that would tell us which model was better than the previous one. We aligned it with the objective. So we wanted to maximize the number of packages delivered to the locker, and we divided that by the locker capacity and averaged it over the number of days to say this was our performance metric that we want to monitor. And now we are ready to look at the model itself. Corresponding to the decision variable and the two unknown parameters, we have three modules in our capacity management model. The first module is the locker demand forecasting module that tells us that predicts how much demand we will have. The second module is the dwell time probability estimation module. It tells us how long a package will stay for in the locker. So this covers the two unknown parameters that we had, and the outputs from these modules go into the third module, which is the ship option capacity reservation optimization, which will give us our final capacity reservations. So let's start with the first module, the locker demand forecasting module. The problem we are trying to solve here is we want to forecast demand for each day, each ship option and each locker. The challenges we face here to traditional time series modeling like ARIMA is the fact that data can be very sparse for less used ship options like a Super Saver, or like we saw in the plot earlier, the number of lockers increases by almost 2 times every year. So by 2021, we will have more than 10 times the number of lockers that we had in 2016. And that means that for almost 50% of our lockers, we don't even have data from previous years. So we cannot predict in an automated fashion when demand will increase during peak time. The solution we had for these challenges was random forest regression. We have 7 random forest models, and the reason we have 7 is because the amount of data I have, amount of information I have for predicting demand for tomorrow is a lot more than the amount of data I have for predicting demand 7 days from now. The inherent clustering within random forest, leaf nodes of the random forest, works well with sparse data, because data from old lockers can be useful for predicting demand for new lockers if they are in the same cluster. And lastly, this model also allows us to incorporate seasonality. For example, we could include the number of packages delivered to homes in the previous year as one of the features of the model. So we know that when that increases, our demand also increases. Let's take a quick look at how this model performed for the 2 instances that we saw earlier. For the same week, 1 week of April 2018, the gray line now shows the prediction from our model, and visually we can see that it is very close to what the actual is in both cases. The first one is locker Ruby and the second one is locker Lambda. So what performance metric should we use for quantifying this? The traditional metric that a person would use would look something like the predicted minus actual, take the absolute value of that divided by the actual, and that gives the percentage error. But what happens if we predict that we will have 2 packages and we end up with just 1 package? This metric would tell us that we have 100% error. But is it important if the locker has only 3 slots? Yes. Is it as important if the locker has 100 slots? Probably no. So the issue that we had with this metric was the fact that it was not aware of the locker capacity. And here we had a tip from a senior statistician in our team, which was to use the same units as the business performance metric. So our business performance metric was the number of packages delivered per locker slot, and we average it by the number of days. We used the same units to come up with our own error metric that was more relevant to our business. We used the predicted predicted demand minus the actual demand, absolute value of that, divided by the locker capacity. And in the scenario that we saw, where we predict 2 packages versus when the actual was 1, this metric would tell us that for a 100 slot locker, our error is 1%, but for a 3 slot locker, our error is 33%, which is what we want. And with this error metric, we were able to quantify these results. For a test period of 2 weeks and 30 lockers in the US with varying levels of utilization, our average error metric decreased from 12.4% for the home ship option proportion method to 2.9% with random forest regression. This was very encouraging, and this gives us a way to predict accurately what our demand is going to be in the next 7 days. So we have covered one unknown parameter that we had, which was locker demand, and we are ready to look at the next unknown parameter, which is how long will a package stay for. So in this module, the problem we want to solve is we want to predict the probability that a package will stay in a locker for 0, 1, 2 and so on up to 6 days. We cut it off at 6 because that is the maximum amount of time that a package will stay in the locker, even if it is not picked up by the customer. To provide a mental model of what we are trying to predict, the probability that a package will stay in the locker on the day of its delivery is 1. But on the future days, the probability becomes lower, and those are the values that we want to predict, like in the image here. The challenges we face are again similar to what we saw earlier, sparse data and new lockers. And the solution is also similar. So, we used random forest classification here, again because it can handle sparse data and data from old lockers become useful for new ones. Since we are interested in the probability values rather than the class prediction themselves, we used isotonic calibration with cross validation to improve the reliability of these probability values. Coming to the performance metric for this one, here it would have been log loss traditionally because we are interested in probability values, but again it is not interpretable. So, if we have a log loss of 0.5 with one method and a log loss of 0.4 with another, what does it mean to the final business performance metric or to our customers? And again we use the same tip, we use the same units as the business performance metric. So, since dwell time probability tells us how many packages will be picked up from the locker, we looked at the predicted number of packages that will be picked up minus the actual number of packages that will be picked up and divided it by the locker capacity to come up with a relevant performance metric for this model as well. And with this we saw an 8% reduction in error against the method in which we were assuming that all the packages would be picked up on the same day. So, now we have a reliable way to predict how many packages will be picked up from the locker. And now we are ready to move on to the third module, which is ship option capacity reservation. We go back to the formulation that we had earlier. We want to maximize the number of package deliveries to a locker subject to constraints on locker capacity and demand. This falls right into the structure of a mathematical optimization problem. We do not hear too much about mathematical optimization in the news these days, and in my opinion the reason is the fact that if we look at the hype cycle of mathematical optimization, it has reached its plateau of productivity, but that does not mean that it is not useful anymore. In fact, now that we have machine learning to predict the inputs to the mathematical optimization models more accurately, this has become even more useful and powerful. So, we formulate this as a mathematical optimization problem that looks like this. It is exactly the formulation that we had earlier written in words translated to equations. The y variables here are the number of packages accepted to the locker. The S index denotes a ship option and the T index denotes a day. So, we want to optimize for the next 7 days. The E variables here are just the number of packages that are already in the locker on the day the optimization is run. So, if I am running an optimization model today, the number of packages that are already in the locker at the beginning of today, those are represented by the E variables. The first constraint is the capacity constraint that we had. The number of packages in the locker should not be greater than the capacity, and that the capacity is denoted by C. The second constraint is the demand constraint, and this demand comes from our first module, which was the demand prediction module, and this goes as input to this model. And the P values here that tell us how many packages will be in the locker are from the second module, that is the dwell time probability estimation module. A unique feature of this particular formulation was the fact that we did not need any additional parameters to prioritize prime shipment packages. And the reason was this. This plot shows the percentage of prime and non-prime packages. Prime is blue and non-prime is orange. The percentage of packages that were picked up on the day of delivery, on the day after delivery, and 2 days after delivery. And based on this, the average dwell time of prime packages is less than the average dwell time of non-prime packages or standard packages. And this is true across all countries and all lockers pretty much. If you are familiar with probability theory, then the number of the dwell time of prime packages is less than or equal to the dwell time of standard packages in distribution. So, a throughput maximization objective, that is maximizing the number of deliveries to a locker, automatically results in prioritization of prime packages here. Finally, the third constraint that we have here is just a relationship between the number of packages that get delivered and the number of packages that are in the locker at a particular point of time. And this constraint and the x variables in this constraint give us what we need, that is the capacity reservations. So, for example, our x for ship option S equal to 2 day and let us say today T equal to today would be 15 slots. We have gone through the model and we are finally ready to see the results of implementation of this model. We built an end-to-end simulation system to test this model. We built a simulation of this whole process of accepting or rejecting a package. And in some ways, this building this simulation system was even harder than building the actual model itself, because we had to emulate each and every nuance of the actual production system. For example, one data set was stored as a decimal in one database and an integer in another. And figuring out that caused the simulation system to behave completely different from the production system. Figuring out such issues and getting past them made us stronger people, for one, and it was also needed to make sure that there was no way we could implement something in production that would adversely affect customer experience. We had a test bed of 30 lockers in the US, again varying locker utilization, and for a date range of 2 weeks in April 2018, we saw a 6% increase in locker throughput. And this was impressive, especially if it is translated to the number of additional packages that we could have accepted. With these results, we started implementing this model in phases on more and more number of lockers in multiple countries. And finally, just before peak 2018, in November 2018, we launched this model on all lockers in all countries, and the results from the implementation. In peak 2018, we saw year-over-year increase of 19.5% in the number of packages delivered to lockers in the US. The improvement was 7.5% in Italy and 16.1% in France. So, that is the number of additional requests that we said yes to, and we were definitely very happy with it. So, after celebrating these results, what's next for Amazon Locker capacity management? We have the rest of this donut to deal with. This year, we are working on a single project that can tackle the gray portion, the green portion, and the white portion at the same time, and we are very excited about it. So, before we conclude, I want to go over some key learnings that we had from this session. The first one is, it is important to understand the business problem setup. It was especially important for us as a science team because we don't get to be involved in the locker operations day to day. One problem can have multiple causes, and it is important to identify which is the biggest cause. There are many underlying issues and assumptions that come up when you question these existing techniques, such as incorrect assumptions and undefined objectives. So, we need an objective that we want to work towards. And aligned with that objective, we also need a business performance metric. We always have constraints on how much we can do. These are physical constraints, hard constraints that we cannot exceed. And after formulating the objective and the constraints, we are able to define decision variables and unknown parameters that we would need to estimate. Machine learning models become very useful for these estimating these unknown parameters. And for us, it was having a performance parameter for ML models that was aligned to the business performance metric made things much easier, both trying to figure out how one model will ultimately affect the business performance metric and for explaining the model to business partners. And the tip we got there was to use the same units as the business performance metric. The key takeaway that I would like to leave with is that machine learning and mathematical optimization, when combined together, can become a very powerful tool. With this, we were able to say yes to millions of Amazon customers. And we were able to start with something that looked like this, a feedback that looked like this, to having a customer love Amazon lockers because she lives in an apartment. This customer loves Amazon locker and Whole Foods because Whole Foods have Amazon lockers in there. And this person here in Vegas who loves Amazon lockers and wishes that there were more things like that in the world. Thank you. I have my email address here. I will be happy to hear any feedback both on the presentation, on the session, and on lockers themselves, either right now or later. We have some time for Q&A, and I'll be happy to take questions.